The intro to assignment 2, blocky 3D animals. So the idea here is that you're going to use cubes to create a 3D animal. And the specification of your animal is here. You have some details that you have to implement. But overall, you're going to have this 3D animal that looks like for example, this video here. This is a fancy version. You don't have to create something this fancy to get an A for this assignment, but be inspired by this is a very cool example, and be creative here. You can create any type of animal or moving creature or animated creature. Sorry. Well, this assignment has the same structure as the other ones. You have a list of bullet points here. Every bullet point maps to the rubric point, and you have details on how to implement these things on every bullet point. Okay? So I won't go over every specific bullet point here in details. I want to talk about the three major ideas that you're going to have to implement in this assignment. The first one being transformations. Which you probably saw in class, is this idea of using matrices to transform vertices, and transformations are, for example, translation, scaling, rotation. The second idea that we're going to talk about today is the idea of animations and how to animate objects using WebGL and JavaScript. And then the third part I want to talk about is how to kind of organize this code into classes to have, for example, multiple instances of the same cube or geometry in a more general way, and how to have each one of them animating in different ways, because this is going to be a key aspect of this assignment as well. Okay, so let's get started. I want to start from our previous project, which is Lab 1. I have here the project we created last week. So I want to make a copy of it. And call it Lab 2. I'm going to rename these files to be Lab 2, or Assignment 2, I'm sorry. And the libraries are going to be the same. And let me open this project in my text editor. And quickly, I'm going to just rename the title of the page to be assignment 2 and also load the correct file here. Okay? Nothing really changes here on the HTML for now, and we have our previous JavaScript. So let me open this in the browser. Okay, so let's get started by just reviewing this code. So if you don't remember, last week we created a vertex and a fragment shader that are very simple here. We get the context, the WebGL context here. We clear our screen with a black color. We define a triangle out of 3 vertices here. We initialize and compile our shaders here. We create a vertex buffer. We bind this buffer to be an array buffer. And then we set up the A position variable in the shader to read from this buffer. And then we send the triangle data to the buffer. We then grab the uniform for color and set the color using this variable here. And then we draw the triangle. Okay? So I want to first talk about the idea of transformations. And I'm going to start with this example of, let's say, rotating this triangle that we have on the screen by 45 degrees, for example. So this would be one example of transformation. Let's first just quickly recap how to define transformations in theory. Okay, so I'm going to open the board here. And start by saying that, or remembering that we can define I'm going to talk about 3 types of transformations here, but quickly, we can define transformation T for translation. And this is a 4x4 matrix that has this format. It's 1, 0, 0, 0, 0, 1. Oh, sorry. 0, 1, 0, 0, 0, 0, 1, 0. And then here we have x, y, z, and then 1. Okay, this is a 4x4. 4x4 matrix. Sorry. Let me fix that. This is a 4x4. 4x4 matrix. We can also define a scale matrix. S, it's also 4x4. It has the following format. It has x here, x, 0, 0, 0, 0, y, 0, 0, 0, 0, z, 0, and then 0, 0, 0, 1. This is our scaling matrix. This is also a 4x4 matrix. Okay. And we can also define rotational matrices. I'm going to just talk about the rotation in the z-axis. And this is also 4x4 matrix. It has a little bit more complicated definition, but let's just quickly recap it. It's a cosine of theta minus sine theta 0, 0. Go back. Zero, 0. Then we have the second row sine theta, and then cosine theta, and then 0, 0. And here we're going to have 0, 0, 1, 0, and 0, 0, 0, 0, 0, 1. Sorry about my handwriting. The computer is a little bit laggy here, so. But I think you can visualize this. Okay, so this is also 4x4 matrix. And why they're all 4x4, right? We're gonna multiply these matrices by a vector v that's normally a 3-dimensional vector, right? X, y, z, right? Why are these matrices 4x4? Well, it turns out, and hopefully you saw that in class, that we normally extend v to have a 4th dimension here equals to 1, because it allows us to combine these transformations here in one matrix by doing something like this. M, for example, equals to, let's say, we can scale and then multiply it by rotation and then multiply it by translation. We normally read this from right to left. Okay, so we have our scaling and the rotation and the translation. We can combine all of this in one matrix called M by having this kind of trick where we extend the matrices to have a 4th dimension, and we also extend the vector v to be to have one extra dimension equals to 1. So then later what we can do something like this. V prime equals to mv, or times v. So by doing that, we are actually essentially doing all these transformations in one single matrix. Okay? So with this review, we'll see that we can create these matrices very easily in JavaScript with the libraries you already have. Okay, so let me start with a simple rotation matrix, and then we can do translation and scaling, and then later actually multiply and do these combinations here. Okay. All right. Let me bring back the code. I'm gonna actually let me not quit this. Okay, let me bring back the code. And so yeah, let's first create a rotation matrix. So how do we create a matrix? Remember, we have a library called Common Matrix C160 that we extended in assignment 0. So we're gonna use the matrix part of this library now. We can create a rotation matrix, right? By doing something like this. Let rotation matrix equals to new matrix 4. And again, this matrix 4 here is defined in the library. So if you go here, if you open this file and search for matrix 4, you see there is a definition of this class here. And this class has a bunch of functions, like set identity, multiply by a vector, and so on. So I do recommend you kind of skim through this file, take a look at the functions. You don't have to understand exactly how they're implemented, but just take a look at the functions you have in your hands. Okay? But you can create a matrix like this, and then one of the functions we're going to use, it's called setRotate. Now what this does, it creates that rotation matrices for us. Right? If I look here, if I look at this function, you can even see the arguments here. So it takes an angle, an x, y, and z. And these y, so these are the rotation axes. Let's see one example of this. Okay. And essentially what these functions do is they create those matrices that we just saw, like with the cosine, minus sine, and so on. They already calculate all of that for you. So here you just have to give an angle. Let's give it, let's say, for example, 90 degrees. Or let's say 45 degrees, right? And let's rotate around the z-axis. So that's why 0, 0, 1. Okay? So if I refresh the page, if I refresh the page, nothing really happens. Let's print out this matrix. This matrix. If I print this matrix, I get here this object. So this second line here. By the way, let me comment out then. Let me actually remove this print here so we don't get confused. We get this object here, matrix 4. So it did create the matrix, right? It's here. It has a bunch of attributes. The ones that I wanted to look at is the elements one. So this elements is a float-to-the-2 array that defines all the values of the matrix. So they are flattened here as one array that has 16 elements. But here you can read that this is the first row of the matrix, then you have the second row of the matrix, the third row of the matrix, and the fourth row of the matrix here. But so what is important is that we can always access the elements by the elements array. So this gives you the elements of the matrix. Okay. And you can access, for example, the first element of that matrix by doing this. All right? Okay. Well, this creates a matrix, but it doesn't really like do anything, right? So to actually perform the rotation, we need to create a rotation matrix in the shader and send this matrix here to the shader. So let's do that. And here I'm going to create this rotation matrix as a uniform variable. I'm going to call it U rotation matrix. Okay. So this is a new variable we are seeing. So GLSL supports matrices that are 4x4, also 3x3 and 2x2. We're going to use matrix 4. And we are using a uniform because we want our rotation matrix to be the same for all the vertices. Okay, so here we have 3 vertices. I want to rotate them by 45 degrees using the same matrix. So that's why it's a uniform. It's the same variable for all the vertices. And the only thing we have to do is, remember, we're going to multiply our matrix by our vector. And by doing this, we are already multiplying all the vertices by that matrix. Okay, the only thing we need to do is that. Okay. So if I refresh my page, well, I don't get anything. And I know it looks weird, but it actually makes sense. You probably don't know yet, but keep in mind that we haven't sent any data to this matrix. So it's using some sort of default value. And it turns out that GLSL starts the matrix, its matrices with all zeros. So what's going on here is that this is multiplying this matrix full of zeros by any vector, so we get a vector 4 with only zeros as well. So we don't see anything because of that. So we have to actually send data to this uniform here. And this is going to be similar to how we did for a color. Indeed, let me actually start by looking at that code. We have this code here that kind of changes the color uniform. So I want to use a very similar approach to do that. And this is going to be something like this. Let me do it here. So we're going to do lat U rotation matrix. I'm going to create a location variable and call GL get uniform location. And I'm going to give here GL.program, similar to, again, I'm similar to this line. But now inside here, I want to do the variable that I want to grab, which is this variable. I want to access this variable, so I'm going to give this here. Remember, we normally, for consistency, we keep the same names here, but it could be anything else. Okay, it could be whatever, it could be random, but we want to keep this name similar. So we now have to do something similar to this. We have to change the uniform value. So we're going to do something like that, gl.uniform. But remember that for every type of variable in GLSL, we have an associated or a respective function to set the uniforms. So this was, for example, a vector 3. That's why you're using uniform 3f. But this now is a 4x4 matrix, so we have to use a specific function uniform matrix 4fv here. And so whenever we create a uniform, we have to find the right function to set it. And here we have the location of that uniform, U rotation matrix, sorry. And second argument is if you want to transpose this matrix or not. We don't want to transpose it, so it's false. And then the third argument is the values that we're going to give to that matrix in the shader. And we're going to grab this rotation matrix, the elements, and send it to the shader. With that, we did everything we need to send the matrix to the shader, and so we should see now that rotated triangle. There you go. So it worked, and we passed this first matrix to our shader and see how simple it was. Okay, we create a matrix and multiply it here. All right. So now, what if we want to translate, for example? Well, we could use a very similar idea, right? So we could do set, instead of rotate, we could say set translate here, which is another function from the library. If you go there, open here, search for it, set translate, it takes x, y, and z as arguments, and this is going to create that matrix we draw before. So here, for example, if you're going to move the triangle by 1 unit on the x-axis, you could do something like this. I mean, note that the name is rotation matrix. It's now actually a translation operation. But let me just do this and refresh the page. You see that now a triangle got translated by 1. Obviously, we should change the name of this variable to reflect the translate operation. Okay? But I just want to show again that you have the same for scaling. And if, let's say, if you want to scale, let me show you actually this function. It takes also x, y, and z, and it creates a scaling matrix for you. And if I want to scale my object down by a half, I could do this, and now I get a scaled triangle. Okay? Cool. But in this assignment, you probably need to combine these transformations and have, for example, a translation followed by a scaling operation, right? So we saw also that in the board that we could do that by multiplying these matrices in a matrix M. And indeed, that's what we're going to do. We're going to actually change the name of this rotation matrix to be a more generic matrix that's going to be the combination of all the matrices. And this is normally called the model matrix. So you're gonna have the model matrix multiplied by a vertex, and it's just a rename to keep it consistent with the common name of this. So this is going to be the combined matrix, which is going to store translations, rotations, and scaling all together. Okay. So now we want to make a model matrix here. Okay. I'm going to change this to be all U model matrix. Actually, let me make sure this is capital M. U model matrix, and here also U model matrix. But also give the model matrix here elements. Let me make sure the name is correct. Oh yeah, the name is a little bit different there. But I just renamed everything, so this matrix here to be called model matrix. Okay. And this uniform to be U underscore model matrix. So we should get the same. Okay, failed to compile. It's not finding. Oh yeah, I changed it here, but I didn't change it here. Let me change it here as well. So now we get the same effect, which is this triangle scaled by a half. Here, right? We are still applying the scaling operation. But now let's combine more than one operation. Let's combine a rotation, for example, and a scaling. So for doing that, we're going to create a rotation matrix. Set rotate. And I'm going to say here 45, 0, 0, 1. And now we're going to also create a scale matrix. And I'm going to say scale matrix dot set scale. Let's say 0.5, 0.5, 0.5. Okay. And now, now we still have to. I'm gonna fix these comments. Say create a model matrix that will store all the following transformations. So we create here. We're going to create a rotation matrix, and here we are create a scale matrix. Okay. So now remember from that whiteboard that we defined the model matrix to be this multiplied by this. But the order we want is scaling first. So actually, we want to do, let me comment this. So we want to do m equals 2. Remember, we read from the right to the left. So we want to do scale first, then a rotation, then a translation. So translate times rotate times scale. And this order is very important. Okay, I'm going to try to show you, like, visualize this. What is the problem if we don't follow this order? But and it has to do with the fact that you want scaling and rotation operations to be done in place or in the center. So you don't want to move your object before doing rotation and scaling. This is going to have like a weird effect. Oh, it's not going to move. It's not going to perform the expected operations. And I encourage you to visualize that. But by keeping this structure, what happens is we're going to perform scaling first, and your object is in the center. Assuming your object starts in the center or in the origin of the world or of the coordinate system, right? You scale the object, it stays still in the center. After the scaling, the object is still centered in the origin. If you rotate the object in the center, it's also going to stay in the center. And then later you can translate it to whatever you want. So if you always do that, then you don't have any problems whatsoever. But if you change this order, you're going to have a little bit of trouble. And you can visualize that later if you want. So, okay. So if I want to multiply in this order, I actually have to do the rotation. I have to do it kind of in the code. It has to be kind of in the reverse order. So it has to be kind of the translate matrix here, and then the rotate matrix, and then rotation matrix, and then here the scale matrix. Okay. We don't have let's create a translation. We don't have a translation matrix, so I'm gonna create one. Let translation matrix translation matrix equals to new matrix 4, and then translation matrix set translate. And let's say I'm gonna keep it all 0 for now, but essentially I want this just to have this structure here when you have the rotation and then the scale matrix. So what we just did was we defined an M as we saw on that whiteboard before. Okay, so we first perform scaling, and then rotating, and then translation. And see that it's kind of weird that we are doing here in the code actually translation first, and then rotation matrix, and then scaling. But turns out to get this order, you have to do this operation, right? So you can actually read here translate, rotate, and scale, right? Here. And this is because these operations, the multiply function, let me find this. The multiply function multiplies this matrix from the right. So, yeah, so just keep in mind we are doing this, okay? And now if you pass the mono matrix here, we already have now these 3 elements combined. So let's start with actually, we have these 3 transformations combined. And now we can do whatever we want in terms of transformations. I mean, we can actually perform in combination of these 3 transformations. So for example, here it is just one translation, right? But if I want to translate and scale down my object, I can do this, right? And if I want to move by 1 unit, I still get my object moved by 1 unit on the x. Okay? So this is how you combine these 3 transformations. Again, this order is really important. So I encourage you to kind of change this order and see what happens with these transformations. It's a really good way to understand understand what happens, first of all. And this has to do with the fact that matrix multiplication is not commutative. So if you change the order of the operations, the results change. Anyways, moving forward, now we can now that it can do any combination of transformations we want, right? We are done with this first topic, which is transformations. The second one that I want to talk today is about animations. How to animate this object, okay? To, for example, let's say rotate by 1 degree every frame. So that can be done using this idea of requesting animation frame in function in JavaScript. So let me create a function here. I'm going to call this update. It could be anything else, but I'm going to call it update. And because this is going to update the kind of our world every frame, okay? But in JavaScript, there is this native function called request animation frame. And here, what I give as argument is the function again. So the function that I just defined, I call it here again. What this does is, if I call this once, JavaScript is going to execute this line with this as argument. So every next frame, this is going to be called again and again and again on every frame. So by doing this, we make this function to be called every frame, which is pretty cool. So for example, here, I could think of this function now as my rendering loop. Right. So far, it's not doing anything, and let's just see it working by printing like loop or something, okay? So, well, I haven't called this, so it still hasn't printed anything. But if I call this at the bottom here, at least once, I'll say that's cool. So now I see the print message every single frame, okay? So it's working. Well, now we have to make sure we transform the object inside that loop. So let's do that. I'm gonna comment this print here, just because it's annoying. And what I want to do is, ideally, I want to have these transformations here happening inside the loop. So also, what I want to do is I want to make sure I draw my scene. So first of all, I want to make sure I draw my scene every frame. Okay. I also want to make sure I clear my screen every frame. So if I do that now, see that I actually moved the draw call from here. So if I do that, oh, there's a problem. GL is not defined. Oh yeah, so this, I know what's going on. We define GL here inside main, and this is a local variable. So we have to make it global. And this is fine because is actually normally how it happens. We can actually define this as null here, and thus outside the main, and that makes it global. So here we just get it like this. This is fine because GL is normally used throughout the whole project, so it's okay to make it global. But also our triangle is here, and just for now, what I want to do is I'm going to make this global as well. Okay, so by removing the lat, I make triangle global, so I can access it inside the update. Okay, let's refresh this, and there you go. Everything's working as before, and this is because but now we are calling it every frame. Nothing's changing because we are calling the same draw over and over again, and we are not changing the triangle. Like, what I want to do is I want to keep this model matrix here a global variable. I want to actually let's make these guys here all global for now. It's gonna make our lives easier. What I want to do is I want to move these calls here. Actually, I'm gonna copy this whole thing and then come back. I'm gonna copy these calls here and put it inside here. After clearing, I wanna do something like this, but I don't want to define the matrix again. Okay, and yeah, I don't want to define these matrices again. I just want to call the set functions on them. Okay, so now what you're doing is we are calling this every frame. We are setting this matrix to be a translation matrix by 0.5 every frame. Note that this doesn't accumulate 0.5 and plus 0.5 plus 0.5. It always sets it to be 0.5, and this also sets it to 45. What we're going to do is we're going to increment these values a little bit every frame. So let me go back down there and let me remove now these calls from here. Okay, and then we have these calls here. Okay. So what happens? Let's see what happens. Well, now we got just the same triangle back as before. Well, and I think this makes sense because now we are sending the model matrix here, but this is done before actually setting the rotation, translation, and scaling. So we have to bring this back, we have to bring this to the rendering loop as well. We have to send this, we set this thing here, and then we have to call this thing here inside. Okay, and because this is always the same, I want to keep this as a global variable, and this part here can be done just once. Okay, we don't need to do this many times. So I want to do this down here. We can do this down here, and you can call this tree model matrix uniform. Okay, and this is going to be global, so we're going to use it everywhere. I think this is a little bit, you don't need to do this all the time. Okay, I'm going to start this with null. And what else? Okay, so this we can. This is already done for us. No, not this one. We grabbed the uniform location down here, so we can use it up there. We can use it here. And so what you're going to do is every frame, we're going to update this model matrix using the elements of our model matrix. So what I want to do is, for example, if I want to, let's forget about these guys for now. Let's just think about rotation. Imagine if I want to rotate our triangle by 1 every frame. I have to, let me create a kind of a rotation z variable here. And imagine I want to do something like this, okay? I want to rotate this matrix by 1 every frame. So every frame I accumulate this variable by 1, and then I set the matrix to have that updated value. Okay? And then let's bring back those multiply calls, because we have to, remember, have to accumulate the transformations in the model matrix. And here we're gonna, so we do the transformations, and then we update shader with the model matrix, and then now by doing this, we are actually combining everything in the model matrix, then sending it every frame. And if translation matrix, rotation matrix, or scale matrix changes, it's going to be reflected in the model matrix. So let's see what happens if you run this code. Oh, there you go. There's something kind of weird, right? It's kind of spinning faster and faster after every frame. And this is because this model matrix gets multiplied here. So it gets this transformation inside it, and then it gets this one, and then it gets this one. In the next frame, this model matrix is not reset, so it keeps accumulating transformations. Specifically, what's going on here is that this rotation is set to 1 in the first frame, right? So then here we run this, we combine this rotation by 1. And then we run the next frame, this is set to 2, or sorry, the first one is 0, the first one is 1. And then we have the next one, rotation z is now equals to 2, and this accumulates a rotation by 2, and then by 3, and then by 4, so that's why you see that crazy behavior. So what we need to do here is set, after rendering the whole thing, we have to reset model matrix. So the next frame, it is fresh again. So then you can call set identity to set model matrix to be the identity matrix. Okay. So if I refresh now, you get the expected behavior. Okay. And now we can also combine, for example, if you want to do the same thing for translation, translation, for example, on X, you can call this 0. We could have the same idea here, right? For example, translation matrix, we're trying to combine now translate, and then we can do translation X here, 0, 0. We don't, and then we do translation X plus equals 1. So what this is going to do is every frame we're going to increment or move the triangle by 1 unit to the right. Okay. It seems that this is too fast, so let me decrease this. Oh, wait. Let me decrease this number. Yeah, and it was just too fast. Okay. So this is it for transformations and animation, sorry. We could do the same for scaling, right? If you want, you could do the same idea here for scaling and have animated scales or animated like scaling effects. Okay, I think the last topic is about how to make this, like for example, if you want to make more than one triangle, right? How to have multiple triangles with independent model matrices and so on. Because right now, if you wanted to have a second triangle here, right, we would have to create a different model matrix if you want them to animate in different ways. So let me show you a common way of organizing this in a very flexible way. Okay, what I want to do is I want to create a class here for the triangle. I'm going to create a new file called this triangle.js, and I'm going to create a class here called triangle. To store the vertices of a triangle. Okay? So what I want to do is I want to copy this line here and just make this class that stores these vertices of the triangle like this. Okay? And also I want to always create them with size 1, or actually with not size 1, in this case they will have actually size 2. But I want to just set these values to be equal to 1. So then when we create them, the triangle is going to take the whole screen here by default, okay? So I did that because now we can easily kind of instantiate multiple triangles, okay? By doing that, we can instantiate multiple triangles. And I have to actually load that script here to access that class. But now what I could do is I could do this equals to new triangle. And then whenever I use the triangle, I have to make sure I give the vertices of the triangle. For example, here, I now have to give triangle.vertices, okay, when I'm sending the data. And now, where else? Let's see. I think up there in our update, let's see, here as well. Okay, we have triangles.vertices.land, and I think that's it. Let me give it a try. Let me refresh this. Hey, there you go. See, it starts with this kind of triangle taking the whole screen, and then the animations are still working. Okay, that was kind of straightforward, but now it gives us some room for making a cool class for the triangle. All right, first thing I want to do is I want to give every triangle a model matrix. So I'm going to say this dot model matrix. Okay, and this is going to be a new matrix 4. So what you can do now is like we can get rid of this matrix here, and I'm gonna move this comment there. Here. And we're gonna have to actually move all these transformations here. Okay. So we want to have one translation and one rotation one scale per triangle. Okay, and you could generalize this to any other geometry, for example, a cube or a sphere or anything you want, or a 3D model. So the only thing that changes in this case would be the vertices, but the idea still remains the same. Okay, so so now that we moved everything there, we have to make sure we have some things right. So let's see. Whenever you use the matrices up there, we have to give the right. We have to access from the class now. So for example, this is going to be the triangle dot rotation matrix, right? And this is going to be the triangle dot translation matrix, and here as well, and here as well, and then here as well. Okay, and then here as well. So now we moved everything inside the triangle. So every single instance of triangle can have this. Is going to have these operations. Okay. So let's see. If you refresh the page, well, it still works. See, we just moved everything inside triangle, which allows us to have a second triangle now. But before we do that, let me create some auxiliary functions here to manipulate these matrices. And this is normally how these things are implemented in other engines. So I'm going to go ahead and do that. You would probably have a function here called, let's say, translate. Right? You would also have a rotate. Let's make a rotate for x, a rotate for y axis, and a rotate on the z-axis. Okay. And translation takes x, y, and z arguments. Rotate takes an angle, and this is going to be an x, only an angle here. Because we're splitting these functions, we just have to give the angle. Okay. And a scale x, y, and z. Okay. Now these functions they actually operate on every specific matrix. So in this case here, you would have this dot translation matrix dot set translate x, y, z. Okay. And here you would have this dot rotation matrix dot set rotate angle, and because this is an x, we're going to do this, and the other ones are very similar, just changing the axis of rotation. So this would be on the y-axis, and this would be on the z-axis. Okay, but this, and then we just give the angle as argument. And for scale, we have something similar, which is this dot scale matrix dot set scale. Right, so we have just making sure the names are correct here. Scale matrix, rotation matrix, rotation matrix, rotation matrix. This is translation matrix. Okay. This is also x, y, and z. So by doing that, now you have these cool, easy to call functions that are much shorter, right? So with this, we kind of substitute these lines here by saying, for example, triangle dot rotate, and here you only give rotate z actually, and here we only give an angle now. See, this is much easier, or gets much cleaner actually. So here we would substitute this whole thing by translate. And this is translation x. And we have to still keep this whole thing here. Right? Let me remove this comment. Let's run this, see if it works. Cool. No bugs. Still works. Right? Okay. Now the last thing I want to do is if I wanted to create a second triangle, right, I would have to do something like this. I would have to come here, instantiate triangle. Let's call this 1, and then a triangle 2, right? And then up there, I have to rename these things. I would have to, let's say, imagine now if I want to do a rotation on 1 and a translation on 2. I would have to call these lines here for 1, and then for 2, and then have this one duplicated for, I have to send the model matrix of the first triangle, then draw the triangle. So we want to have another function because you would have to duplicate kind of all these calls here per triangle. So because of that, I want to create a function draw here that takes a triangle and performs the draw operations, which are, first of all, we update the model matrix, right? We then, this still includes that part. See how this is actually dependent on the argument here, right? Then we draw, and reset. So by doing that, now we can easily call, draw triangle 1 and draw triangle 2, right? And this goes here, triangle 1, then is set the triangle 1 here, model matrix. We update using triangle 1 here, update the uniform, then we draw the triangle 1 vertices, and you reset the triangle 1 model matrix. And in the second call, we're going to do the same thing, but for triangle 2. And see how actually cool clean this code looks, okay? Let me just double check if I don't have to do anything else down there. Yeah, so this is the same here. Oh, there is now this part is still, so the buffer data call, this that sends the vertices to the GPU is down here. So we definitely want to call this per triangle, right? We definitely want to call this per triangle. So before drawing an array, I have to send the data from that triangle, right? So I have to update the buffer per triangle because they have different set of vertices, okay? So but by doing that, I now have this very flexible and reusable draw function that I can use to call two different triangles. And note that what we expect to see is the first triangle rotating around and the second triangle kind of translating to the right. Okay, let's look at this. Let's see if it works. Wow, there you go. See, this triangle is going to the right and the other triangle is rotating around the z-axis. That's pretty cool. It worked without any bugs, right? And now you could still combine multiple operations or multiple transformations to your objects. That's what I had for today. With this week, what you have to do now is take these ideas to create a 3D block animal. And I would start by creating maybe a cube function that's similar to this one, right? That the only thing that changes is the vertices here, and they should represent a cube, a whole cube. So you could create a new file here called cube, and then have a class cube here that is very similar to this one, but with only the vertices changed. And here you would have all the vertices of the cube, but this whole thing here would remain exactly the same. Okay? And that should allow you to draw cubes as opposed to triangles. And then you could kind of start drawing multiple cubes to make your enemy. And because you can animate in any way now, then you could make this code very flexible. Okay, so good luck on your assignment, and see you later.